XENONNT detector now operates as the most sensitive dark matter hunting instrument ever constructed. Dark matter comprises 85% of the universe's total mass, remaining invisible except through its gravitational effects on visible matter, and recent results from the Lux-Zeppelin experiment have excluded WIMP dark matter particles above 9 Cc. The Roman lead shield surrounding the XENONNT chamber create the pristine conditions necessary for detecting these elusive interactions, blocking background radiation that would otherwise overwhelm the faint signals scientists hope to measure. The gravitational evidence for dark matter's existence comes from observations that should be impossible if only visible matter existed in the universe. When astronomers study rotating galaxies, they find that stars on the outer edges move too fast to be held in orbit by the gravity of visible matter alone. Something invisible must be providing the additional gravitational pull needed to keep these galaxies from flying apart. That something outweighs all the visible matter in the universe by more than 5 to 1, creating cosmic scaffolding upon which ordinary matter assembles into the structures we observe today. Computer simulations reveal how dark matter forms vast filaments stretching across space, with dense nodes where matter accumulates to form galaxy clusters. These simulations accurately predict the distribution of galaxies we see when we look deep into space, but only when they include 5 times more dark matter than visible matter. Remove the dark matter from these models, and the universe becomes a sparse, uniform soup with no galaxies, no stars, and no planets. The cosmic web of dark matter creates the framework that allows the universe's architecture to exist. The connection between dark matter detection and the matter-antimatter asymmetry puzzle runs deeper than most people realize. Some theoretical models suggest that the same physics responsible for creating the tiny imbalance between matter and antimatter in the early universe also governs how dark matter particles interact with ordinary matter today. If these models prove correct, detecting dark matter could provide crucial insights into why the universe contains matter instead of pure energy. The experiments searching for dark matter particles might simultaneously solve 2 of the most fundamental mysteries in cosmology. The XENONNT experiment achieved a 5-fold improvement in background suppression compared to its predecessor, establishing new limits on how dark matter particles might interact with ordinary matter. Based on 97.1 days of operation, XENONNT demonstrated world-leading sensitivity that surpassed all previous experiments in its ability to detect hypothetical dark matter interactions. The ancient Roman lead provides the ultra-low radioactive contamination levels that make this unprecedented sensitivity possible, creating detection conditions that modern materials simply cannot achieve. When a dark matter particle theoretically collides with a xenon nucleus, it transfers only a tiny amount of energy, producing flashes of light and electrical signals so faint that even microscopic amounts of background radiation can overwhelm them completely. The Roman lead blocks this background radiation by providing shielding with contamination levels orders of magnitude lower than contemporary materials. The 2,000-year underwater aging process reduced radioactive isotopes to virtually undetectable levels, creating the pristine environment necessary for detecting individual dark matter interactions. Scientists have expanded their search beyond traditional WIMP candidates to explore other potential dark matter particles. The Tesseract experiment targets particles about 100 to 1,000 times lighter than WIMPs, using transition-edge sensors that operate at temperatures around 8 millikelvin. These sensors can detect energy deposits as small as a few electron volts, opening new territory in the search for low-mass dark matter particles. Tesseract's initial tests found no dark matter signals, but established unprecedented sensitivity for detecting interactions involving extremely light particles. Axions represent another promising dark matter candidate that requires entirely different detection methods. These hypothetical particles would interact with magnetic fields in ways that convert them into detectable photons. Researchers have developed techniques using squeezed coherent states of light to amplify the conversion probability between photons and axions, potentially leading to more sensitive detection experiments. Teams of scientists have made significant progress toward using quasiparticles to hunt for axions, which could constitute a significant fraction of dark matter. The theoretical models guiding dark matter searches have evolved significantly based on the latest experimental results. Supersymmetric theories predict specific ranges of masses and interaction strengths for WIMP dark matter particles, but recent known results have forced theorists to explore alternative scenarios. Some models now focus on dark matter particles that interact primarily through forces other than the weak nuclear force, requiring new experimental approaches that go beyond traditional xenon-based detectors. Multiple experiments around the world are converging on similar sensitivity levels, creating opportunities for cross-validation of any potential discoveries. The core experiment in Italy, also protected by Roman lead shielding, searches for neutrinoless double beta decay while maintaining sensitivity to certain types of dark matter interactions. The combination of results from different detector technologies and target materials provides complementary information that strengthens the overall search strategy. Recent detection candidates and anomalies have generated excitement throughout the dark matter research community. Several experiments have reported events that could potentially represent dark matter interactions, but these signals remain below the statistical threshold required for definitive discovery claims. The XENONNT collaboration has observed excess events in their electron recoil data that could indicate new physics, though the significance falls short of a discovery-level detection. The success of using ancient Roman lead for dark matter detection has demonstrated that archaeological materials can enable scientific breakthroughs that would be impossible with modern materials. The underwater preservation process created lead with radioactive contamination levels that 21st century technology cannot replicate, regardless of the purification techniques employed. This unprecedented collaboration between archaeology and physics has opened new possibilities for future experiments that require materials with properties that only time can create. The future of cosmic archaeology. Scientists around the world now recognize that their most ambitious experimental goals may depend on materials that have been aging underwater or underground for centuries. The success of the Roman lead experiment has created unprecedented demand for ancient materials that possess the ultra-low radioactive contamination levels required by cutting-edge physics research. The 30 tons of Roman lead that enabled breakthrough sensitivity in dark matter detection experiments represents just the beginning of what could become a systematic search for archaeological materials with unique scientific properties. The 2025 landscape of particle physics experiments reveals a field pushing toward detection sensitivities that modern industrial materials simply cannot support. The U.S. Department of Energy has committed $71 million in funding across 25 high-energy physics projects, with the aim of leveraging quantum information science to explore fundamental questions about the universe. These experiments require shielding materials with background radiation levels that are orders of magnitude lower than what contemporary manufacturing processes can achieve. The funding supports development of quantum sensors and detection technologies that will need even more sophisticated protection from environmental interference than current experiments. The success of the Archaeological Physics Partnership that produced the Roman lead shielding has inspired similar collaborations worldwide. Teams of scientists are now actively searching for underwater archaeological sites that might contain metals suitable for scientific applications. Shipwrecks from different historical periods offer materials with varying degrees of radioactive decay, allowing researchers to match specific archaeological finds with the requirements of particular experiments. Bronze Age shipwrecks might provide copper with different contamination profiles than Roman-era sites, while medieval vessels could offer iron with unique purity characteristics. International protocols for responsible acquisition of ancient materials have evolved rapidly to address the ethical complexities of these partnerships. The archaeological community has developed guidelines that require extensive documentation of historical context before any materials can be transferred to scientific applications. These protocols mandate that physicists must demonstrate that no suitable modern alternatives exist and that their proposed research addresses questions of fundamental scientific importance. The agreements also ensure that archaeological teams receive adequate compensation and resources to support their own research programs. Experiments like Tesseract demonstrate how archaeological materials continue to enable new frontiers in physics research. Tesseract is planning to relocate its experiment underground to the Modin Underground Laboratory in France to reduce cosmic interference, with operations expected by 2029. The experiment will search for dark matter particles as light as 10 MeV, requiring detection systems with sensitivity levels that demand the purest possible shielding materials. Ancient metals could provide the background suppression necessary to explore this previously inaccessible mass range for dark matter candidates. The growing intersection of history and high-energy physics has created entirely new fields of interdisciplinary research. Material scientists now study ancient metallurgy techniques to understand why certain historical processes produce metals with properties that modern industry cannot replicate. Archaeologists are incorporating materials analysis techniques developed for particle physics to gain new insights into ancient trade networks and manufacturing practices. The collaboration has generated research opportunities that neither field could pursue independently. The integration of quantum technologies with particle physics represents another frontier where ancient materials could play crucial roles. The Department of Energy is funding projects that use quantum information science technologies, including superconducting qubits and atomic sensors, to enhance experimental sensitivity. These quantum-enhanced detection systems require environmental isolation that exceeds even the demanding requirements of current dark matter experiments. Ancient materials with centuries of radioactive decay could provide the ultra-quiet environments necessary for quantum sensors to achieve their theoretical performance limits. Current discoveries continue to reveal new applications for archaeological materials in modern science. The ResNova project uses Roman lead recovered from shipwrecks to shield detectors, searching for neutrinos from astrophysical sources. The Herald and Spice detector modules are being developed to diversify detection methods and cross-validate potential dark matter signals, each requiring specialized shielding materials with specific purity characteristics. These projects demonstrate how ancient materials enable multiple experimental approaches to fundamental physics questions. The search for materials extends beyond shipwrecks to include archaeological sites on land that might have preserved metals under conditions that prevented contamination. Ancient mines that were sealed and abandoned could contain metals that have been isolated from cosmic radiation for centuries. Historical smelting sites might yield slag or byproducts with unique chemical compositions suitable for specialized applications. The systematic exploration of archaeological materials for scientific applications has become a recognized field that combines historical research with materials science. The economic implications of using archaeological materials for physics research have created new funding models that bridge scientific and cultural preservation goals. Physics experiments provide resources for archaeological excavations while gaining access to irreplaceable materials. These partnerships generate scientific discoveries that serve both physics and historical research communities, justifying the investments required to develop and maintain these unique collaborations. The XENONNT experiment continues to operate with the unprecedented sensitivity that only the Roman lead shielding makes possible. The ancient metal blocks gamma rays and other forms of radiation that would otherwise overwhelm the detector's ability to distinguish genuine dark matter interactions from background noise. The 2,000-year underwater aging process that reduced radioactive contamination to virtually undetectable levels has enabled scientists to probe deeper into the fundamental mysteries of existence than ever before possible. This extraordinary collaboration between archaeology and physics has demonstrated that the answers to our most profound scientific questions might require resources that transcend the boundaries of any single discipline. The marriage of ancient preservation and modern detection technology has opened new pathways to understanding reality itself. The Roman lead that once served commercial purposes in the ancient world now guards the most sensitive scientific instruments humanity has ever constructed, protecting experiments that could reveal why the universe contains anything at all. The convergence of ancient preservation and modern detection has produced results that validate this extraordinary collaboration. XENONNT achieved a 5-fold improvement in background suppression compared to previous experiments, establishing world-leading sensitivity in the search for dark matter interactions. This breakthrough became possible only because Roman lead provided radioactive contamination levels that modern materials cannot match, no matter how sophisticated the purification techniques employed. A Roman merchant sailing the Mediterranean 2 millennia ago had no idea his lost cargo would become essential to this scientific achievement. The lead. Ingots that sank off Sardinia were destined for construction projects that never happened. Instead, they aged underwater for 2,000 years, allowing radioactive isotopes to decay to levels that enabled the most sensitive particle physics experiment ever constructed. The story connects ancient commerce with modern physics in ways that reveal how preservation, chance, and human curiosity can converge to address the universe's most fundamental mysteries.